Alright, so there's a special set of vectors that we need to talk about called the unit vectors. And so to set this up, let's think about fundamentally what defines a vector. Well, to have a vector, there'd have to be two pieces of information, right? I need to know the magnitude of the vector, and I also need to know its direction. So I know that vectors have both magnitude and direction. So what unit vectors are is they're a special subset of vectors that have a magnitude of 1 unit. And so if I have some general position vector, r, right? I can talk about a unit vector, r hat, so my little symbol here, with this little symbol notation, instead of being an arrow to mean the vector, it's a little hat symbol. It's basically like a triangle without the bottom edge. So r hat here is the unit vector that I can build from vector r. And you see that the way that I build that is I basically take vector r and divide it by its own magnitude. So I get the unit vector, right, r hat, by taking vector r and dividing it by the magnitude of vector r. This gives me two things, right? So one is, it tells me that r hat has a magnitude of 1 unit, right? If you go ahead and calculate out what the magnitude of r hat is, it's fairly easy to show. But sure enough, you're going to get that that has a magnitude of 1. The other thing is that r hat points in the same direction as vector r. So my unit vector r hat, again, it's a unit vector because it has a magnitude of 1 unit, and the reason it's called r hat is because it points in the same direction as vector r. So r hat is the unit vector that points in the same direction as vector r. And so we'll use that notation to talk about a particular unit, or a unit vector that goes with a particular vector. Now, there's a special set of unit vectors that we'll care about, and these are the Cartesian unit vectors. And they're basically two ways that you can sort of lay them out. Our textbook uses I hat, j hat, k hat. There are other textbooks that would use x hat, y hat, and z hat. It doesn't matter, they're interchangeable. They mean the same thing. And the idea is that each of them have a magnitude of 1 unit. I hat, or x hat, points in the positive x direction. So again, magnitude, 1 unit, direction of I hat is positive x. Direction of j hat is positive y. Direction of k hat is positive z. So it's easy enough to see the directions if you happen to use the x hat, y hat, z hat grouping. It's not really any more difficult with I hat, j hat, and k hat. Just remember that the I goes with x, j goes with y, and k goes with z. Now once I've got the reason why these particular unit vectors, the Cartesian unit vectors, are so useful is because it's fairly easy to write any vector that I want in 3-dimensional space using these 3 Cartesian unit vectors. So I can use them to tell me how much I need to go back and forth, how much I need to go up and down, how much I need to go in and out to build any vector I want. The way that's best described is in what's known as unit vector notation. So unit vector notation, again, notice this isn't a unit vector. It's simply giving me vector A in what's known as unit vector notation because I'm telling you a component and a unit vector. So AX, AY, and AZ, again, those are the X, Y, and Z components of vector A. And then the I hat, j hat, and k hat are our 3 Cartesian unit vectors. So what each of these are telling you, so here's, again, back to thinking about my little coordinate system here, where I'm letting positive x point to the right, positive y point up, positive z is pointing out towards us. Well, I can take any vector I want. So here for an example, let's just think of this vector A that I've drawn, which happens to have an x component of negative 1.5 meters, a y component of 2 meters, and a z component of 0 meters. So what that tells me is the negative 1.5 meters as the x component tells me that vector A points 1.5 meters in the negative x direction. So you can think of how far I have to go, and then the sign and the unit vector are telling you in what direction. So this piece in my unit vector notation is telling me I need to go 1.5 meters in the negative x direction. My middle piece here is telling me I need to go 2 meters in, again, positive y. So the positive j hat tells me this is in the positive y direction. And again, there's 2 meters in the positive y. 0 meters k hat says I don't need to move at all into or out of the page. So vector A, because it has a z component of 0, lies in the plane of the board here. It doesn't point out towards us, or it doesn't point into the diagram at all. And so this is one of our ways when we talk about reporting a vector using unit vector notation. It's a fairly straightforward procedure where you're just going to tell me what the component is times the unit vector that goes with that component, and then we just add all those things together. Now, of course, I can also talk about the unit vector in the direction of vector A by using exactly the same formula that we saw before, only this time instead of talking about a position vector, vector r, I'm talking about a more generic vector, vector A. But it's the same idea. The unit vector, A hat, is equal to vector A divided by the magnitude of vector A. So again, we'll use our example here. And the first thing is, well, our picture, so this is going to have a magnitude of 1, just like our 3 Cartesian unit vectors. So A hat has a magnitude of 1 unit, and it's going to point in the same direction as vector A. So it lies along the same line that vector A does. Now obviously, if I want to calculate what A hat is, the first thing to do is basically to get the magnitude of vector A. Calculate the magnitude of a vector, I'm going to Pythagorize. Pythagorizing in 3 dimensions means that I want the square root of the x component squared plus the y component squared plus the z component squared. And so using my x component of negative 1.5, y component of 2, z component of 0, plug all that in, and I get the magnitude of vector A happens to be 2.5 meters. So now I can take that magnitude and calculate my unit vector by taking the x component of vector A dividing by the magnitude, times I hat plus y component of vector A divided by the magnitude j hat plus z component of vector A divided by the magnitude times k hat. So again, I'm still giving the unit vector vector A in unit vector notation here. But when I calculate it out, what I get is the unit vector A hat is going to be negative 0.6 I hat plus 0.8 j hat plus 0 k hat. So a couple things to notice. One, again, is this is actually unitless, right? Our unit vector is unitless because I took a meter divided by meter. Those canceled out in all 3 of the components. The other thing is this needs to have a magnitude of 1. So it's always straightforward to check and make sure that your unit vector has a magnitude of 1 by taking the square root of x component squared plus y component squared plus z component squared. Sure enough, you do that here, you get 1. So vector A hat is a unit vector. So these are the subtle differences between talking about a unit vector and talking about a vector in unit vector notation. And so we'll continue to sort of make these points of emphasis within class as we go forward.